Okay, a photon with a wavelength of 1.5 times 10 to the negative 8th meters emitted from an ultraviolet source into a vacuum. Okay, look. First question. Calculate the energy of the photon. So for question A, look, this is going to help you on the AP exam. To calculate the energy of a photon, there's an equation, H times F, where H, who's got that? I hear some audio. Turn it off. I hear Planck's, this is Planck's constant. Okay, this is Planck's constant right here. You don't have to memorize it. It's going to be on your equation sheet or your constant sheet. Planck's constant is 6.63 times 10 to the negative 34 joule dot second. And then there's also an electron volt version, which I don't have that one memorized here. I got the sheet right here, though. The electron volt version is 4.14 times 10 to the negative 15 electron volt dot second. Now, so we're given the wavelength. Look, we're given the wavelength. How do we get the frequency? Well, there's an equation for that. This, velocity equals wavelength times frequency. So frequency is going to be velocity over wavelength from an ultraviolet source. So look at ultraviolet. Hey, ultraviolet source. How fast does ultraviolet radiation travel? Speed of light. So the V becomes C. So that's C over wavelength. This is going to be 3 times 10 to the 8th meters per second. Now, look at this is going to be 1.5 times 10 to the negative 8 meters. So this gives us a frequency of, where did I write it down? What did I do right here? Oh, darn it, I didn't write it down. So that's going to be what? Sorry, dudes. 3 exponent negative 8. Oh, sorry. 3 exponent to the 8 divided by 1.5 exponent to the negative 8. 2 times 10 to the 16th. Oh, yeah, I could have done that in my head. 2 times 10 to the 16th hertz. So you take this, plug it in up here. So the energy of the photon, so let's do it in joules. 6.63 times 10 to the negative 34 joule dot second times the frequency, 2 times 10 to the 16th hertz. But what's a hertz? A hertz is 1 over a second, so the seconds cancel, and we find out that the energy of this, of one photon of the radiation is 1.323 times 10 to the negative 17 joules. Not bad. Was that a hard question? Not if you have the equations. If you know the equations, you're fine. Now, second question. Second question wants us to find the de Broglie wavelength, which I've never, ever, ever talked about, but I'm talking about it now. Look, the idea with the de Broglie wavelength is that everything travels in a wave-like fashion. Hey, if I took a baseball right now and threw it to you, guess what? As the baseball flew through the air, it would have a wavelength to it. The ball flying through the air would be traveling, in a wave-like fashion. The equation, so when they ask you for the de Broglie wavelength, and dudes, you don't have to memorize this. It's on the AP equation sheet. The equation for de Broglie wavelength, so put a little D for de Broglie. The de Broglie wavelength equals Planck's constant over the momentum. Remember, P is momentum, okay? P equals momentum. What's the equation for momentum? You just took an equation quiz. What's the equation for momentum? mv. So this becomes H over mv. Look, that's how you calculate the de Broglie wavelength. But we got to figure out the velocity of this electron. Now, how do we get the velocity? Okay, let's go over here. I'll put it in this little box. Kinetic energy equals 1/2 mv squared. So the velocity is going to be 2 times kinetic energy over m. So that's going to be 2 times this answer. This is kinetic energy. That's the energy of the electron, which is going to be kinetic. 1.323 times 10 to the negative 17 joules, right? And then mass of an electron. Do you have to have that memorized? No, it's on the test. That they give you the mass of an electron. 9.11 times 10 to the negative 31 kilograms. So you get the velocity as it's basically like 5.4 times 10 to the 6th meter per second. Take that, plug it in for velocity. Here's the mass of the electron. Plug that in for m. We got Planck's constant, so it's going to be 6.63 times 10 to the negative 34 joule dot second. Mass of an electron, 9.11, 10 to the negative 31 kilograms. Velocity, 5.4 times 10 to the 6th. It's just a bunch of plugging in. That's all it is. And then the wavelength comes out as 1.35 times 10 to the negative 10. De Broglie wavelength. Dude, equation's going to be given. All you got to do is plug into it. Easy. All right, final question, and then we're done. Last thing for the year. Describe an experiment that illustrates the wave properties of this electron. So here's what you could do. We talked about the double slit experiment. You could take a beam of electrons. So you're going to set up a picture like this. Create two slits. Over here is going to be some sort of like detector. Okay, so we'll call this like, I don't know, it's not a screen. We'll call this, what's the word for this? Just call it a detector. Okay, so you have a beam of electrons that come in, and you're going to define your terms. So the distance between the slits is d. From the slits over to where the detector is L. And then you're going to get a pattern of maximum, minimum, maximum, minimum. Because that's what waves do. Waves can interfere with themselves, right? So we talked about this, the double slit. So you get this pattern of maximum, minimum, maximum, minimum, maximum, minimum. You do that, they're going to go like this. They're going to go, oh, part C, smart kid. 100%. Spaldo out.